Hello, and welcome to our product redesign of a stapler. My name is Nathan, and I will be presenting along with Jonathan, Alan, and Sean. Staplers are used for semi-permanently joining multiple pages of paper together. Staplers are often preferred over paperclips or binders for organizational purposes, since paperclips can easily be undone accidentally, and binders are large and bulky and best suited for large-scale projects. After aligning the pages to be joined under their stapler, the operator would press down firmly on the top of the stapler, forcing a single staple through the pages until it reaches the bottom of the stapler, where the metal guides bend the staple in order to ensure that the staple will not fall out once the operator releases the pressure and returns the stapler to its resting position. The primary customers of staplers are office employees who constantly need to staple multiple pieces of paper together. These primary customers require a method to properly align their sheets of paper and bind them together without much physical effort or time consumption. The secondary customers of staplers that we will target is the typical college student, who does most of their work on their computer, but occasionally would need a stapler for printed assignments or longer homeworks. This customer drives the need for cost efficiency. Both customers require a simple device that does not take up significant desk or backpack space, is safe and easy to use, and economically friendly.
Hi, so I'm going to get into our functional analysis, taking a quick look at our FAST diagram. You can see on the far left our task function is fasten paper, and that's followed by some main supporting functions like load staple and plant staple, and those are followed by a few more supporting functions on the far right. And then you can also see our primary supporting functions at the bottom of the middle column, and those also have a couple of their own supporting functions.
The two most feasible assembly sequences are shown in fishbone diagrams. These sequences were chosen based on ease of assembly and the ability to test the functions of the sub-assemblies in the stapler throughout the assembly process. As seen in both assemblies, the process begins with the bottom base followed by attaching the anvil and hinge spring sequentially. Following sequence 1, the staple carrier is then attached, followed by the staple feed subassembly, which includes the guide rod, then guide spring, then slide foot. The carrier cover is attached, then the pivot pin is inserted. The drive blade, then top housing are attached to complete the assembly. Following sequence 2, the staple carrier and carrier cover are attached after the base subassembly. The pivot pin is inserted, then the staple feed subassembly, which includes the guide rod, guide spring, and slide foot. The drive blade and top housing are then attached to complete the assembly. To determine the more favorable assembly sequence, this chart was made to compare the efficiency of each in the 5 categories listed in the first column. For the ease of transferring and handling, both sequences were scored at 2 because components in both only have one insertion direction, so they could be difficult to orient. For the ease of locating parts, both sequences were scored at 2 because most components in both sequences have a unique geometry which indicates what its purpose is in the assembly. For the ease of fastening and joining, sequence 1 scored a 3 and sequence 2 scored a 1 because in sequence 2, if the pivot pin is inserted first, the slide foot will face resistance to insertion into its location. For ease of testing subassemblies, sequence 1 scored a 2 and sequence 2 scored a 3 because in sequence 1, the staple feed subassembly is put together before the pivot pin is inserted, so it will be hard to test as it is not fixed to the base. For the ease of assembling in parallel, both sequences scored a 2 because most components can be assembled on parallel lines of insertion in both sequences, but a few must be inserted perpendicularly.
Moving on to our function component mapping matrix, each part of the stapler was analyzed as to which function it served. These functions are the ones shown in our functional analysis diagram that Johnny talked about. Parts were added or eliminated from the stapler if they did not support one of the basic functions that we had outlined. Next, a bill of materials was made based on the new CAD model that we created. Manufacturing and assembly processes were chosen for each part. Based on those processes, a rough cost estimation was performed. These costs included the material cost of the part, the process cost, the assembly cost, and the tooling cost. The numbers on the chart were based off the geometry of each part and the previous cost estimations done during the homework. All of the costs summed to $10.46 for our total manufacturing and assembly cost. A quad chart analysis was also performed on each part of the stapler. The functionality and estimated cost of each part were considered. Each part was assigned either high or low on functionality or cost based on the bill of materials and function component mapping matrix. The analysis shows that a redesign still needs to be done on the anvil, hinge spring, and staple pusher in order to reduce cost. According to the chart, the carrier cover can be eliminated completely from our design.
Getting into our product family design, we start in the top left with functional differentiation. You can see that most of our functions from the FAST diagram fall under the same for both customer groups, with 3 of them that are differing. Next to that is our component commonality table. You can see that all of our components fell under platforms except for our base, which is our one module. And then at the bottom there, we have two bases, the blue being our original and the red being our product variant, and you can see their differences from the callouts. Next, getting into our product family assembly diagram, you can see the top assembly shows the differentiation is immediate when the base is added, and then the bottom displays a delayed differentiation to shorten product lead time between the two product variants.
Here you can see a chart for calculating the total manual assembly time of the current design based on handling and insertion. We chose to redesign some components in order to reduce this time, as you can see at the bottom, by about 10 seconds, which was a 14% decrease from the original design. Here you can see the before and after CAD screenshots, which show exactly where the design changes were. For our platform components, we consolidated the top housing and carrier and changed the shape of the top housing in order to reduce handling time and assembly time of unnecessary parts. For our module component, we changed the shape of the base in order to provide better grip during manual assembly and reduce total time. Here you can see a chart for calculating the total automated assembly cost for our staple feed sub-assembly before and after redesign. We reduced the cost by 0.82 cents, which was a 31% reduction. Here you can see the before and after CAD screenshots, which show the design changes of each component. The diameter of the end head and shaft of the guide rod were increased in order to prevent overlapping during automatic feeding. For the same reason, the width of the wall on the slide foot perpendicular to feed direction was increased to provide more stability during feeding.
Now for our first process selection, we're going to start with the top housing, which was redesigned for the manual assembly. And you can see that the material there is ABS, which is a thermoplastic, and the process that's chosen based on the chart on the left is going to be injection molding. You can also see a drawing with some dimension callouts as well as the selection parameters on the right. Now for the process selection for the guide rod, which was changed in our automated assembly, you can see that the chosen material is going to be aluminum 6061, and the process that was selected is going to be machining based on the chart on the left. And then again, you can see a drawing with some dimension callouts and the selection parameters shown on the right.
For the parts identified in the process selection section, an in-depth cost analysis along with the redesign was completed for each. The DfM Pro software was used to identify issues with our CAD that would make manufacturing our parts harder. The first part analyzed was the top cover. Initial part analysis gives a cost estimate of 0.907 cents from the analytical method. This part was then analyzed using DfM Pro, and issues with undercuts and draft angles were found. The draft angles around the pinhole and a curve at the top of the part were added to get rid of this problem. The undercut was solved by removing plastic overhanging from the back of the part. This redesign did not change cost much according to our cost estimation, but it did improve manufacturability. The second part analyzed was the guide rod. Before changes, the part cost was calculated to be 0.313 cents. The DfM Pro analysis showed us issues with an inner radius being too small and no draft angle on the end face of the section to be turned. Also, issues with the part's length were found. The part is too long and slender and might bend while machining. The draft and inner radius were changed to the recommended values, and the part was thickened in order to help it from bending while the part is being machined. A tailstock will also be used to support the length of the part during machining. The changes were found to be negligible from the analytical method of calculating the part's cost. In the Hub's part cost analysis, the part became about 50% more expensive to manufacture between the changes. It's also worth noting that Hub's is showing that the part is much more expensive to manufacture than the analytical method predicts.
For the product service system, we could design a staple delivery app that would save the customer time, money, and would save the environment. Other added benefits would be if the stapler breaks, you could order a new one right away from the app, and it is an app, so it can be updated easily without any customer contact. For conclusions and design critique, benefits of the new design would be that the product is cheaper, assembly time, manufacturing time, and the manufacturing cost would all decrease slightly. Although there are some concerns with this new design, especially the potential for injury to the customer. If we could change our design at this point, I would recommend starting with redesigning the staple distribution mechanism rather than simply the size and shape of external parts within the assembly. This concludes our presentation. Does anyone have any questions?